sound problems. So it is my pleasure to announce the first speaker of the day. It's Pedro Ribeiro, in a joint work with FCMA24-Pedro. The title, as you can see, is Poisson's summation formula and index transforms.
Thank you very much for the kind introduction. This talk will be a bit mixed, because I will talk about the main results. The main slides will be myself talking, but then Semyon will make some expert comments on the kind of stuff that I will talk about. So the plan for this talk is to first introduce the Riemann-Zeta function, and then to present a formula due to Bernd, Dixit and co-authors concerning Bessel functions, a proof that in a separate work related with this, I found using the Kontorovich-Lebedev transform, and then the questions that arise from this new proof and the variants of this proof concerning the summation formulas attached to the index of a class of special functions. And then I will address some further questions. Okay, first I usually begin my this kind of presentations presenting the first protagonist of this kind of stuff, which is usually the Riemann-Zeta function. As most of you, perhaps all of you know, it is usually introduced in a course, Calculus 1 course, first course in analysis, real analysis, this series, which of course converges absolutely if I take the parameter s as real when the parameter s is greater than 1 by the integral test, and diverges, of course, if the parameter is less or equal than 1. The interesting case s equals 1 due to Nicolas-Loresme, the divergence of the harmonic series. Of course, this was a great problem in the 17th century, how to evaluate the Riemann-Zeta function at the 2 or 4 or 6, etc. And there was this conjecture by Bernoulli that it was around 1.6 or something. It was they expected some kind of convergence and some values, and Euler discovered that in fact when we put the exponent equals to 2, then we have this relation. We have a relation between an infinite series of this kind and geometry pi. This was the discovery that made Euler famous, the solution of the Basel problem. And then Euler, in a later paper, actually in the same paper, generalized this kind of thing. Like he discovered that the zeta attached to all even integers will be a power of pi to the whose power is the same as the argument of zeta. And this guy here, this B2k, is the Bernoulli number. It's a well-known rational number, usually coming from combinatorial problems. Euler, of course, knew about these kind of numbers because they appeared in a previous book by his mentor, Jacob Bernoulli, but actually these kind of things were known to Japanese mathematicians previously. But since Japan, since the Tokugawa, since the shogunate Tokugawa was isolated from the rest of the world, nobody knew about these contributions of Takakazu Seki. Okay, so let me, before going to the technical part of the talk, mentioning a long time interest of Professor Petronillo concerning the zeta function. I was a student in the year 2020 and 2021 at functional analysis course and special functions course, orthogonal polynomials and special functions course, constructive approximation, something. What was the name of the course? But the part that Petronillo taught us was, and Kenyon, was the orthogonal polynomial. And he was not obsessed, but he really enjoyed the problem of the zeta function attached to odd integers. As you can see, I mean, when the argument is even, we have a power of pi. And you know, since Lindemann, 1882, that these kind of things are transcendental, because pi is transcendental, and the Bernoulli numbers are rational. So, okay. But the problem is when the argument of the zeta is odd, what can we say about that? About arithmetic nature? And Petronillo really liked this problem. And he thought that the theory of orthogonal polynomials would be essential to solve this kind of this great problem. of course, Apéry in 1979 proved that zeta of 3 is irrational. And then all kinds of things are known, like there are infinitely many values, odd values, for which zeta is irrational. We don't know which, but there are infinitely many. And we know by the Zudielian that at least zeta 5, zeta 7, zeta 9, or zeta 11 is irrational, at least one of them, at least one. Which one? Nobody knows. From zeta 5 to zeta 69, it is also known that there are at least 2 values from that are irrational. But which one? Nobody knows. And in fact, there is a proof that zeta 3 is irrational using Legendre polynomials. And perhaps due to these polynomials, perhaps would be essential to solve the limit, okay? This has a limit, which is gamma. Nobody knows anything about this constant, but Conway said that he would like to live long enough to see a proof that this guy was irrational. And Pedro once said me that he would like to live long enough to see a solution of that zeta 2n minus 1 was irrational. So this kind of thing, this is a tribute to him. So I would like to mention this, his interest in these things. So let me now explain briefly that after Euler introduced the zeta function, then Riemann complexified the Riemann zeta function. Now the called Riemann zeta function, before was Euler zeta function. And what Riemann did was like, he turned the product of gamma of s times zeta of s, when it makes sense, of course, as an integral of this type. Of course, this integral only makes sense when s is a complex number whose real part is greater than 1. Because if it's less than 1, this guy will explode at the origin, right? You have x to the s minus 1 at the origin. If the exponent is small, it will explode. But in fact, this integral can be deformed in a way that it remains valid for all complex values of s. And that's what Riemann did. He took this integral, it took a deformation of the path. Instead of the real line 0 to infinity, or the half real line, it took another path. Now the integral would make sense, and he proved a lot of things. He proved that the Riemann zeta function is analytic everywhere except with a singularity at s equals 1, where it has a simple pole. It has simple zeros, so-called trivial zeros at the negative even integers, and it satisfies the functional equation of this type. This actually says that, say me anything about zeta function on a part of the complex plane, then this tells how it behaves in the other part. And as you can see, the subset of the complex plane that remains invariant under this equation is precisely, what is it? Is a vertical line equals to 1/2, because 1 minus s becomes real part equals 1/2. It stays on the real line, on the vertical line. And if you take s equals 1/2 plus it, the vertical line with real part equals 1/2, it stays invariant under this transformation. And that's why the line of symmetry, which is given by the real part of s equals 1/2, is called the critical line. It's where all the symmetry of the Riemann zeta function relies on. And in fact, from this functional equation that Riemann discovered, one can easily check that this function here, pi to the minus s over 2, gamma s over 2, zeta s, is real, not complex value, as assumes real values when we are on this line. And this will be quite important somehow in a later slide, okay? So this function is real on this line because of this guy here, due to this invariance. As you can see, 1 minus s when we are on a critical line is the same as the conjugate of s. So this says precisely that the function here, eta s, is real. Not complex, real. That's important to introduce transforms here. Now I will talk about a bit of special functions, namely the other protagonists, the modified Bessel functions. If you take the usual Bessel differential equation and you slightly change the argument, if you turn x into ix by multiply by I, you get this modified Bessel differential equation. And if you formally solve it using power series, you get one of the solutions, which is this, the modified Bessel function of the first kind. And you can also impose another solution by taking this combination, and you get the Macdonald function, the modified Bessel functions of the second kind. And these are the protagonists of this talk, the special functions that will be mostly important in this talk, which are motivated by this problem from physics. Okay, there are other things like the first solution to Bessel's differential equation blows up at infinity. But the other one, due to the restriction, it goes down. It decays exponentially fast at infinity. Okay, both solutions have this behavior, this drastically different behavior. But as you all know, when we restrict the argument of the Bessel function, the index nu, perhaps to 1/2, we can recover elementary functions. So in some limiting cases, we always have a relation between elementary functions. In this case, hyperbolic sine of x, when the index is 1/2, and in the case of the Macdonald function, this e to the minus x. Okay, now a bit scary, this formula, but in 2018, Bernd, Dixit, Kim, and Zaharescu, motivated by the work of Ramanujan and Korslyakov, proved a general summation formula involving the product of Bessel functions. This was kind of motivated by a way to generalize some claims of Ramanujan, but the thing that they got was this. We have on one side a series involving a product of the modified Bessel functions, I and k. Note that these converge because of the condition x greater than y. Let me see why. Okay, k nu goes exponentially fast to 0. But this guy goes exponentially fast to infinity. But since the exponent of k nu is greater than the exponent of the argument of I nu, it is okay. The convergence is assured. But the difficult part is this one. Like, you have these arguments, and then the second series will involve the hypergeometric function. And they were interested in fixing some parameters, nu and nu in both cases, and get new formulas and recover old formulas from this kind of thing. And one that you get, not by fixing nu, but by letting y tends to 0, is this one, is a formula due to Watson. So when you take y to 0, the modified Bessel function of the first kind will become elementary, will become like this guy, something that does not depend on y. And then you plug in this formula, you plug in y equals 0 in this formula, the hypergeometric function will become a rational function by reduction formulas, and you'll get this, which is a very important formula due to Watson. Very important in the analytic number theory, this formula. It appears in the theory of Epstein zeta functions. It appears in Ramanujan's lost notebook somehow. And this is a particular case that they emphasize that it is a particular case of that formula. But their proof is very complicated. That means, just remind something. They use an analog of Voronoi summation from due to Guinan, whose conditions are very difficult. Actually, Guinan does not prove the formula, it's only formal. And they also do not prove, they indicate a proof, I think, but the proof by Guinan is a bit sketchy, not completely complete or rigorous, I would say, but it's correct, of course, because they don't need the full strength of Guinan's statement. They need a weaker one, which is, of course, correct, is due to Korslyakov. So all the steps are valid. They use evaluation of Hankel transform due to Korslyakov, which is also kind of difficult. And they use several transformation formulas for the hypergeometric function, which are not very easy to use. They use simultaneously several transformation formulas. But in fact, the corollary previously stated, this one here, Watson's formula, can be obtained by their formula, but as an independent proof, namely from the reflection formula for the theta function. And was because of this that when I started working on studying the number of zeros of some combinations of the Dirichlet series, I found this integral transform, which is in a table compiled by the supervisor of Semyon, Marichev and Prudnikov and Savishenko, which represents the product of two Bessel functions, which appears in the formula of Bernd, Dixit, and the co-authors, in this way. So I immediately thought that if I wanted to reprove the formula of Bernd and co-authors, I would put a sum here on the left-hand side, justified interchange between the sum and this complex integral, and then sum over n, this guy here, and this Bessel function here. I will put the things. So if I want to recover their formula, note that I knew k nu. I just need to use this integral, and let's see what we get. So I put the formula, I sum that I knew K knew. I put the sum inside of the integral, justifying, of course, appropriately that I can do that, but it's not very difficult to do because these gammas are quite nice. We have two gammas above and one gamma below. The decay is very nice due to Stirling's formula. And then I need to evaluate this sum. But this sum, we already met this sum. Let us recall from Watson's formula. Note that in this formula, which was a corollary of the formula of Bernd, Dixit, and co-authors, we have a Bessel function k nu multiplied by a power of n, and you have the same thing here. The only difference is one, is like, in this formula it is assumed that the real part of the power of n is greater than 0, and here we don't know. But note that, let us see the conditions of the integral again. C, so the real part of the argument of the integral, is between a negative number, minus 2, real part of nu is assumed to be positive at the beginning, and 1. So, in particular, it's valid when C is between minus 2 real part of nu and 0. I can assume C to be negative. And if it is not negative, assume that it is positive, I can shift the line of integration with Cauchy theorem. The function is analytic, so it's okay. I can shift always to when C is negative, when the real part of the argument S is negative. So, if the real part of the argument is negative, this means that this guy here above is positive. So I can apply this formula. Applying this formula, of course, with the substitutions, like this x becomes x minus y, this nu becomes s over 2, and this nu becomes minus s over 2. Note that there's no problem in turning nu to s over 2 because k minus nu and k nu are the same. So I can put this exactly in this template by replacing s over 2 by minus s over 2. Doing these substitutions and applying Watson's formula, which can be proved independently, is a formula from the 20s, we could get that formula automatically, using just an integral representation which resembles an index transform, which will be the talk, which will be the subject of the next slides. And using these kind of things, the same technique, we could prove several formulas that the other authors did not consider. For instance, involving products of MacDonald by MacDonald, modified Bessel function of the second kind by modified Bessel function of the second kind, and then by another Bessel functions and mixing the different Bessel functions. And in particular, you could get some new formulas like this. I ask here, like, does this formula look familiar? It is familiar because when you take y equals 0, we recover Watson formula again. But these kind of formulas are new in this sense. So in fact, using a kindly, slightly different argument, we could also prove, but I'm not going to show. You'll see why the formula, because it's very long, of a formula involving products of Bessel function, but with different indices. Note that in the formula of Bernd, I can show again. It's here. All the index of the Bessel functions need to be the same. Need to be the same. It's crucial. And in our formulas involving these mixed Bessel functions as well, the index needs to be the same. But you can take a variant of this kind of arguments to prove formulas when the index are not the same. But as I say here, and in fact there is a formula like that, a formula that they conjecture, Bernd, Dixit, and co-authors. But I now say, like, making an excuse à la Fermat, like the proof is very long to contain in these slides. The formula is very long to be contained in these slides. It's an excuse à la Fermat. So let me now, the proof, the simple proof that I found used, I can show again the integral, used an integral with respect, as you can see, with respect to S. So the integral, in fact, as a product of gammas, as this exponent, which is inoffensive actually, and then the main part of the integral is that it is with respect to the index of the MacDonald function. And these kind of things, these kind of integrals, are alike the Kontorovich Lebedev transform. Why? Because I can fix a C, like C is between this guy and 1. You can fix C equals 0. And then rewrite this integral as an integral, as a real one. Right, like when S appears, you always write like S equals to minus IT, for instance. And then the integral becomes from minus infinity to infinity. just changing variables. And if you do these kind of things, you take the integral that the point of departure and you make this change of variable, you'll get something like this. You get something of this type. Okay? You get a function multiplied by the McDonald function evaluated at whose index is purely imaginary. And this is usually how the Kontorovich-Lebedev transform is introduced. So taking the integral as a point of departure again, the previous integral, you take c equals 0, and you get this. So our way to prove the formula of Bernd and get new formulas was actually to take a Kontorovich-Lebedev transform as a point of departure. Like we have the modified Bessel function here, we have an integral with respect to the index, and then you have this function that you need to calculate the transform. But this was the point of departure. And then the next question was like, if I put a function here instead of this product of gammas and etc., if I put a function which has a number theoretical interest, like the Riemann zeta function, what can happen? In fact, what is the question? This is a question from 2022 actually, but we now connected with this different word. What is the Kontorovich-Lebedev transform of this function that we introduced at the beginning, which is real? Remember that due to the functional equation, this guy here assumes real values on the critical line when the real part of S equals 1/2. So let us try to, this will be a real function when restricted to the line. Let us try to calculate the Kontorovich-Lebedev transform of this real function, okay? And we have a lemma somehow, which says that if you calculate the Kontorovich-Lebedev transform of this guy here, which has a number theoretical interest, you'll get this series. Of course, this result is mainly computational. It's like, it's technical in a sense. But using this kind of information, you can get new transformation formulas involving the modified Bessel function evaluated at 1/4. How? Note that this guy here is invariant if you replace t by minus t due to the functional equation. This guy here is also invariant and you replace t by minus t because it's a property of the McDonald function. K nu of z is always k minus nu of z. So if you replace t by minus t, it's okay, it's the same guy. But this one, if you replace t by minus t, it's the same as you replace xi by 1/xi, right? If you replace t by minus t, you get xi to the it. But this is the same as 1/xi to the power of minus it. So what does this say? This says that this thing here is somewhat invariant when I replace xi by 1/xi due to the symmetries of this integral. And this gives a new summation. Note that we have an invariance in these both cases. The only thing that changes on the left-hand side and right-hand side is the xi. Below, it becomes 1/xi, and above it becomes xi. So we can get, this formalism works not only for the Riemann zeta function, for any Dirichlet series. You can get a lot of new formulas just by looking at the Kontorovich-Lebedev transform. This is one of many examples. And now I will introduce somehow the last part of the talk, which says the following. Note that in the beginning, motivated by something about zeros, I won't describe that, a technical thing of number theory, we were mainly interested about sums of products of Bessel functions, but with respect to the argument. Note that the variable of summation is exactly the argument of the Bessel functions. But the same question can be asked, what about if the argument of the Bessel functions is fixed, like the index is here, but the variable of summation is the index? That's the question. What can we say about sums of this kind? Like the sum now is not under the argument, with respect to the argument x. X and y are fixed now, x is fixed, but the variable of summation is precisely the index, I and alpha. What can we say? And there's a result due to Semyon. This does not work very well, but the reference is here. The reference is at the end. Sorry for that, cannot be read here. In my computer it works just fine, but Semyon proved that if you take the sum of the Bessel function with respect to the index, you get this kind of transformation. He used Poisson summation formula and well-known Fourier transform of the Bessel function. And it could also do the same for products. Now the formula becomes a little bit more complicated because it appears a k0 here, while here appears an exponential, an elementary function. But our question next was, can we do the same when we replace the Bessel function by a more general function, the Whittaker function, which actually appears in orthogonal polynomials? It is related with Laguerre polynomials and generalizes this function here. Can we do that? And the question is that we could do that. Let me just introduce the function in question. The Whittaker's function is usually introduced as this combination of confluent hypergeometric functions. But the thing is like, we have to, in the case of the Bessel functions, we have only one index. The thing that I want you to remember is that in the Whittaker function, you now have two indices. And if you fix one, mainly the first, and you set equals to 0, you recover the Bessel function. That's the only thing that I need you to know. And the question was, can we repeat? Let us look again to Simeon's formula. The formula is with respect to the index of k. Can we do the same with respect to the second index of the Whittaker? That's the question. Let us see. These are only properties of the Whittaker function. When you take the first argument equals to 0, you recover the Bessel function. And then we take the argument differ by 1/2, we get an elementary function. That's only basic properties. Okay. The question is, we have this reduction formula. And we have the formula from 2008 that Simeon proved using k, I, and alpha of x. The question is, can we prove something for the Whittaker? Note that such a formula will reduce to the formula that we know, because when you take mu equals 0, you can recover the formula obtained by Simeon. And in fact, we could prove this formula. Now that note that in the formula previously, with respect to the Macdonald function, what appeared at the right-hand side was an exponential, elementary function. Now we have a symmetry that appears a Whittaker function. And this is the main result. And note that as particular case, you can get this. By fixing mu equals 0, you can recover the formula from 2008. And the main idea of this formula, the main idea of the proof, was using this Fourier transform, which was actually the only way that we could compute that was by invoking this Mellin-Barnes representation, and then compute, if you want to compute the Fourier transform of the Whittaker function with respect to index, in a certain point you need to compute the Fourier transform of this product of gammas, but this is well known, and inverting everything, you could get the formula, which we could not track on the literature, but it's interesting, and there is another, there are other familiar formulas, cousins of this formula that you could get. For instance, we could get formulas with respect to index of products of Whittaker functions, and then products of gammas and the Whittaker function as well. But we don't know what we didn't address this case, like when the indices of the Whittaker functions are the same. We could get a formula when the first index and of both Whittakers are symmetric. We could get a formula for that. But in this case, is more difficult. It's much more technical. And another question that I would like to leave. Previously, I talked about the Kontorovich-Lebedev transform of the Riemann eta function, like the complete version of the Riemann zeta function. I could compute that. But can we do the same when we replace the Bessel function here by the Whittaker function? I don't know. It will be very nice to obtain a formula of that in that setting. Okay, me and Simon are very grateful for the invitation, of course. Petr really was a dear friend of us, so it's a pleasure to honor him in this conference. So it's okay. I don't know if Simon would like to okay. Expert comments now.
Thank you very much for your invitation. It's a bit great. It's indeed a great opportunity to pay tribute to our friend Zé Carlos. And I personally remember our numerous discussions about such kind of problems when I arrived to Portugal And as you understand, we are representing our area of integral transforms and special functions. Despite centuries old, it's still active and developing many interesting classical things. And as you can see, this promising contribution of Pedro gives significance of, in particular, Kontorovich-Lebedev transform, which is indeed a basic transform of a new class, which I started to investigate early 80s. And then 86 years ago, it was introduced by two physicists, Kontorovich and Lebedev, relating to some problems in mathematical physics. At that time, it was just curiosity, really reciprocal formulas of new kind, which involves integration with respect to parameter of a Bessel function. Before the end of 19th century, Meller did similar stuff with spherical functions. It's kind of Meller, we call Meller-Fock transform. And then Kontorovich and Lebedev applied to mathematical physics, and then some around 50 years, it was just time to time appeared in mathematical papers. And I got this problem to develop this kind of transformations with this nice kernel, you see, McDonald function of pure imaginary index. And then we understood that we can generalize this kernel because we know perfectly the structure of so-called hypergeometric functions. And this we come to the Mellin transform technique, as far as you, perhaps you know how it is good involved in a series of special hypergeometric functions, which is a structurally, its Mellin transform contains only the ratio of the product of gamma functions. This was a great demand of Wolfram Research Corporation, Mathematica, which we were involved in 80s to create algorithm to analytical calculation of integrals. And as you can now use Mathematica as users to do this, but it's still, they have a great demand to involve index transforms. At that time, we introduced this notion in 80s, index transform, because you understand of this integration by index. So my former supervisor is now working in Wolfram Research, so this is still contacting time to time, trying to involve these index kernels, which Mathematica doesn't know how to calculate such kind of integrals because there is no good algorithm, only general formulas we can involve, and this was done with our group in 90s, 80s, and later, involving Mayer G function, which is one of the more general special functions you can find on internet, really all information, necessary information. And then we proved, and also it started from American mathematician Wimp, he did formal proof of such reciprocal formulas involving G function, and I simplified these formulas, and we introduced this notion index transforms, which are now is worldwide used, and hopefully it will be more involved. And now you see the Pedro's contribution, very promising contribution to involve this in number theory, because 40 years ago I was criticized, why is this beautiful formula, where you can apply this? And now we have great applications. And we have more demand to use in number theory, because this classical group, starting from Ramanujan, centuries old results, and then Bernd, you know perfectly, I hope, 5 volumes book, Lost Ramanujan Notebook. We still are discovering very classical old formulas. We can give more fruits, more applications, more good, interesting results. And of course, I'm now working in we are interested in number theory questions, classical, of course, classical irrationality problems, and so on. And still discovering new index transform. What means discover new transform? How to give a life to a transformation. So it could be inverted. It could be inverted. It could be given a reciprocal inversion formula, concrete, explicit, Of course, we are studying involving functional analysis, LP spaces, L2, LP, Parseval equality, and so on. And then finally, we come up with these great number theory problems, this infinite series involving Whittaker, McDonald, Bessel functions. It seems for the first view quite technically complicated. But please compare what Ramanujan started and how great contribution he did, and still we develop such classical results. Then we come also to discrete class of index transform and still have interesting problems. Of course, it involves also approximation theory results. So we are trying to employ many general theory in approximation functional analysis to, of course, rigorously justify all our steps of proofs and so on. So it's not only formulas for computers, not only. So it's interesting theory, still developing, and hopefully we can succeed in some stuff very difficult in number theory, as far as you know, irrationality, transcendental problem, and so on. And I think it's our goal for near future, and of course such young mathematician as Pedro will continue, and also we will involve more people, more interested people in such topics. Thank you very much for your invitation.
Thanks very much to Pedro and Semyon. Is there any question or remark?
Sorry for
is just to say that I have many questions, technical questions, but okay, the time is out. Let me just remark something. Pedro commented something regarding irrationality and Petronilo, and it's true. During the last 10 years of his life, we worked very hard without productions, without papers. Indeed, we studied very hard on the rationality of certified. And we have two wrong proofs with two different approaches, and I still have in my hands the paper worked in LaTeX with the sentence that we cannot prove and that I cannot prove still. And it's just that we have two wrong proofs and many hours of study in parallel with our work. So this is extremely nice topic. And Pedro and Jakubovic are essentially, well, they are really good. Jakubovic is the most fortunate people in Portugal. He has the best student in Portugal. Unfortunately, it's hard for his student obtain a position in Portugal. Yeah, the last one is in the private sectors, and we are very concerned regarding Pedro. That is extremely sad, but it's the reality in some places of the world. But Pedro and also the previous student and Jakubovic are extremely good mathematicians. Thank you very much for your time.
Thank you.
Any other question or comment? So congratulations for your nice work, and let's thank again.